Today we'll present on the paper Win with What You Have, QoS-Consistent Edge Services with Unreliable and Dynamic Resources. This is the outline of our presentation. To begin with, what do we mean by edge services? In simple terms, it means that the services are delivered from resources located closer to the end user, for example, mobile servers or IoT devices. We want these services to be consistent with the QoS levels, and for that, we customize the execution of equivalent microservices, which we'll discuss in the upcoming slides. But these resources are mobile and have less energy reliability compared to cloud servers. Thus, we require mechanisms that can dynamically adapt to the available computing resources, network conditions, and user requirements. The edge servers communicate to the cloud through edge nodes, which have smaller computing capability, but they provide lower latency because they are closer to the user. This is one of the key differences between edge and cloud services. But edge servers have less computing capability and higher failure ratio. For example, if mobile devices move out of communication range, or if a speech recognizer fails due to excessive noise. There are numerous sensors and data processing methods at the edge, and based on that, a previous model called MOLE was developed based on the concept of equivalent microservices. Let us say that the task is to find if a room is empty or not. For this, multiple resources like camera, motion sensors, or GPS tracking on the phones can be used. These are called equivalent microservices for this particular task, and they can be executed in two ways. One is a failover pattern, which means one after the other, or a speculative parallel pattern, which means simultaneously. But for each task, these strategies are predefined, and thus they can deliver inconsistent results when the client is in different environments. So in this paper, we develop an approach which uses a feedback loop to monitor the performance of these edge services and generate dynamic execution strategies. The motivation behind this is that by executing equivalent microservices by different strategies, we get different QoS values. This paper has threefold contributions. First, we talk about the system design. Then, we formulate execution strategies and compare the QoS values. And finally, evaluate the efficiency of our system. Before we go on to the system design, we understand some challenges in providing edge services using some examples. First, consider an online retailer using cloud service to manage its data. In this case, if there is surge in traffic, extra computation and resources are required. In this case, we have multiple data centers that we can configure to meet the requirements. But consider an edge service provider that has a self-driving car as its client. For this, we need real-time data, but this is unreliable as it is dependent on the availability of sensor data, which can be affected by weather or by congestion in communication links. So, we need some techniques to manage this scarce and dynamic resource. Consider another example where we can use edge computing for effective city traffic management. An example of this is managing opening and closing of extra lanes depending on the traffic that way. This has various issues like there is lack of standardization in the data from various sources like camera or detectors because they are in different formats. Or let's say in high rush hours, the response gets slower due to limited computability. One more example is to detect potential fire present in dissimilar environments. This has two major limitations of edge resources. Firstly, which is dependent on devices, and secondly, on the environment. Let's consider a mobile device, and it is difficult to predict or control this resource because the users can move away or use the devices at very random times. Or the second one, that is environment, let's say for example, an office building can have heat sensors or higher computing edge servers, but places like forest can have very limited energy sources and less computing capacity. So here, as we can see, there are IoT nodes, which let's say are the smoke detectors, which is the edge layer. There are users on the edge layer, as well as there are some sensors. And all of this data is sent to the cloud layer, and at the end, the cloud makes a decision, and then the authorities are informed. Now, MOLE is an reliability enhanced edge service, which means that the service developers specify the execution strategies for equivalent microservices, which include failover and parallel strategies. Now, we can use this MOLE concept in the two examples explained before. which uses equivalent microservices as follows. So in the traffic management example, we have GPS tracking device, we have motion sensor, or we have cameras. Similarly, in the detecting fire example, we have data from the temperature sensors, we have data from the smoke detectors, as well as from the cameras. Now, a drawback of the mole strategy is that once an execution strategy is used to develop the edge service in particular environment, that same strategy may not work in all the other environments, and so we need a more dynamic system. Before we move on to the algorithm, let's see what execution strategy means. So it is basically a sequence of operations of microservices which can be omitted if, let's say, one of the previous services succeeds. Some of the examples are listed here of the many possible execution strategies. So for 5 services, let's say A, B, C, D, E, there can be failover, which means one after the other, all of them, or a speculative parallel strategy, which means that all of them are executed together, or let's say a combination of these. But there's a chance that there can be duplicate strategies. So to avoid that, we need to keep these 3 observations in mind, which is that the failover strategy is not commutative, but the parallel strategy is, and both speculative and failover strategies follow associative property, etc. Now, to find out the total number of possible strategies, let's consider an example wherein we take numbers from 1 to 9 and take only the odd numbers, which means 1, 3, 5, 7, 9, which means our data set is of 5 digits, and there are 2 operators, plus and minus. Now we need to select 3 numbers from this such that by using 2 operators, we can get a result of 20. And this can be done in 3 steps as shown here. First, we select 3 digits from the 5 given and allot them at the respective positions, which will mean that P5, 3 arrangements are possible. Then we fill the 2 slots of the operators, which can be done in 2 square arrangements. And then finally, we alter the precedence of the operator slots, and this can be done in 2 factorial ways. This similar strategy can be used to derive the formula given below.
Now that we have determined all the possible strategies, let us have a look at estimating the QoS of a strategy. We cannot estimate the QoS by running the strategy only once, because there are chances that any microservice could fail or succeed. Instead, what we do is that we estimate the average QoS of running the execution strategy multiple times. Coming to the QoS attributes, we have 3 major QoS attributes. The first one is the cost, which is the amount of energy consumed to execute the microservices. The second one is reliability, which is the probability of finishing an execution successfully. And the third one is latency, which is the time taken to execute the microservices. What we prefer is the strategy with lower cost, lower latency, and higher reliability, which is also known as trust. Coming to the notations, we have capital M, which is the set of equivalent microservices. We have RM, which denotes the average reliability, LM, that denotes the average latency, and CM, that denotes the average cost. We have a few assumptions. The first assumption is that although multiple devices can provide a microservice in an edge environment, our system only selects the one with the best QoS. The second assumption is that once an edge device receives a service execution request, it charges the full execution cost irrespective of whether the execution is to succeed, fail, or terminate midway. Coming to the QoS estimation algorithm, we have to calculate the overall reliability. We calculate the overall reliability by the provided formula, which is 1 minus the probability term. So how did we get this formula? We know that R is the probability of successful execution. So the probability of success is nothing but 1 minus the probability of failure. So in our case, the probability of failure is when all the microservices of an execution strategy fail. So that's how we got that term. And coming to the overall latency and cost calculation, we convert the strategy into a tree structure with 3 different types of nodes. The first type is a leaf node, which is an equivalent microservice. The second type is a sequential node, which has 2 child nodes, the right child and the left child, as shown in the figure as well. And the third type is a parallel node which has two or more child nodes. We also have an example picture here in the slide. Let's go ahead and calculate the timelines of all the microservices. So starting from the root, we recursively calculate the timelines of all the microservices. Tau denotes a timeline and it has three attributes M, S, and E, where M is the microservice, S is the start time, and E is the end time. For a leaf node, M points to its microservice, start time is set to 0, and the end time is set to its latency. Now coming to a sequential node, we calculate the timelines of the left and the right child nodes first. We then find the longest end time of a microservice that belongs to the left child. We add the longest end time to the start and end times of the right child. Why do we do this? Uh, this is because the right child of a sequential node is only executed when all the microservices in the left child fail. Now coming to the parallel nodes, the timelines of all its children are generated. We know that a parallel node has two or more children, so we calculate the timelines of all its children. Now coming to the overall latency calculation, we initialize the latency to 0 and sort the timelines based on their end times in ascending order. For each service in the set, we add the product of the end time and the probability term. This probability term is nothing but the probability that the ith service will succeed and all services before the ith microservice will fail. Now coming to the calculation of the overall cost, we initialize C to 0 and for every microservice add the product of the cost of M, which is denoted by Cm, and the probability term. This probability term is nothing but the probability of all the services that have their end time before the start time of M and all these fail. Coming to the system design, it is an extension of MOLE where we extend the gateway to support QoS-Consistent edge services. There are four important components: client, gateway, devices for executing services, cloud-based service market for providing service scripts, and microservice executables. The client sends a service request to the connected gateway. Each service has a unique service ID. The gateway follows the service script describing the data flow and the QoS requirements. The service scripts needed by the gateway can be downloaded from the cloud-based service market and cached locally. If the client requests for the same service again in the future, the gateway can process the request locally without contacting the cloud. Now coming to the enhancements over MOLE. In MOLE, the service script specifies the priority list of microservices. The script is uploaded to cloud to get the execution strategies. The enhancement is that the execution strategies are generated locally at the gateway in our edge computing. Another enhancement is that the edge gateway has a feedback loop which has strategy generator, a collector for recording QoS characteristics, and a strategy executor. The execution strategy generator retrieves the QoS characteristics from the collector and outputs and it basically outputs an execution strategy. The strategy executor invokes the microservices and the collector updates the QoS characteristics. Coming to the QoS utility index, the QoS satisfaction model of cloud is binary. The service either satisfies the requirements or not, so it is either a 0 or a 1. For edge, the binary satisfaction model is not applicable because developers using edge applications have no choice. They need to use the available edge services. We find the services that approximate the requirements closely. We have capital S, which denotes the set of all execution strategies, and capital Q of S, which is the estimated QoS value for a strategy S. A strategy S is Pareto optimal if and only if no other strategies in S can improve any of the QoS attributes without worsening the remaining QoS attributes. New metric is introduced to understand how Pareto optimal strategies satisfy the QoS requirements. So this new metric is the utility index. So when the estimated value is less than the requirements, then we say that it is unsatisfied and the utility index is negative for this scenario. If the estimated value is equal to the requirements, then the requirements are satisfied and the utility index is 0. And if the estimated value is greater than the requirements, the utility index is positive. So the possible values are negative, 0 and positive. Now coming to the strategy generation, we have M, which is a set of microservices. So if the number of microservices is less than or equal to threshold, we use exhaustive search. So what do we do is that it calculates the estimated values of the QoS performance and chooses the strategy that has the maximum utility index. And in the other case, when the number of microservices are greater than the threshold, we use approximation algorithm and not exhaustive search because it takes a lot of time and there's a lot of latency. So in the approximation algorithm, we sort the microservices by utility. We initialize the execution strategy ES to the first value of the sorted microservices. We loop through the microservices and we keep removing the first value of the sorted list and add it to the estimated strategies ES1 and ES2. ES1 is a sequential execution and ES2 is a parallel execution. At the end, we reassign the strategy that has the maximum utility index to ES. We can also have a new heuristic. In the current two heuristics, we get an execution strategy that has all the M microservices. So in the new heuristic, we can take a subset of the microservices, but in that case, we will have to face a few consequences whenever a used microservice is not available. Then we have to go to the next uh, execution strategy that has the highest utility, but that might not be available because of data constraints. So it is always better to have execution strategies that have all M microservices.
Now we will dive into the evaluation. The paper has two different sets of evaluation. On the first set, we evaluate our approach against previous approaches. On the second set, we evaluate the real world performance of this proposed system. On the first experiment set, we have three different experiments comprising of 11 different configurations. Here, average CLR means the average QoS estimates of cost, latency, and reliability, and the delta means that value range of those QoS attributes. In the first experiment, we vary the average QoS estimates. In the second experiment, we vary the delta. Third experiment, we vary the number of equivalent microservices. And these are the QoS requirements which needs to be met on all the configurations. If we look at the utility index distribution of all the configurations, in the experiment A, in the figure A, we vary the average QoS estimates. The blue line indicates the higher QoS estimate indicated by the blue line. The more strategies fall into the higher utility range. That means more strategies out of total possible strategies have satisfied or exceeds the QoS requirement specified, which results in higher utility index values. And similarly, for higher range, higher amount of equivalent microservices results in higher utility index values. And as the paper claims that generated strategy through approximation heuristics can yield more consistent QoS, in order to prove that, this experiment compares the existing predefined strategies with our newly proposed algorithm. Using above configurations, each configuration has been run using 4 different algorithms. From the figure, we can clearly see that the number of QoS satisfied services are much higher compared to the predefined strategies. Till now, the configurations we have seen, there are maximum of 5 equivalent microservices. What if we have more than 5? How does our approximation algorithm perform in such scenario? This experiment simulates such scenario. As we see in the figures, when we increase the number of equivalent microservices, the generated strategies through approximation algorithm outperformed the predefined strategies such as sequential and parallel. In the second figure, if we observe closely, we can see that approximation algorithm always produces positive utility index values, which means most of the strategies generated exceeds the QoS requirements, and for sequential it just satisfies, and for parallel it's mostly negative. That means most of the strategies didn't satisfy the QoS requirement. And one more thing to observe is uh, for parallel there are much lower negative values because of the penalty k assigned for unsatisfied QoS attributes, hence producing much lower utility index values. And one more thing to observe is, in order to do this, our approximation algorithm takes a little bit of execution latency, that is a little bit of more time to get the strategy out of it, that is 10% extra time needed for that. And we move on to the second set of experiment to evaluate the system in the real world setting. In this evaluation setup, we have a edge gateway, and it has a task to get the ambient temperature. For this task to accomplish, we have 3 different microservices. The first one is using the temperature sensor deployed on the Raspberry Pi, and second one is estimating the ambient temperature using the CPU temperature, and the third one is by querying the web service for the location and using the location to query another web service to get the ambient temperature. So now we have 3 equivalent microservices to accomplish the task. Please take a closer look at this A, B, C as we use these notations in the further slides. Using the above evaluation setup, we compare the generated strategy QoS with the predefined default strategy. In this experiment, our goal is to improve the QoS attributes compared to the previous predefined strategy. That means to reduce the cost and latency and increase the reliability. For this experiment, we use 100 service invocations, that is asking for what is ambient temperature 100 times per time slot. And here the default or the predefined strategy used is the speculative parallel execution, and our approach using feedback loop produced a different strategy, that is the sequential execution. And in the results we can see that the generated strategy indeed reduced the cost and latency and increased the reliability. So by this experiment we achieved our goal of improving QoS by generated strategy compared to the predefined strategy. Till this point, we haven't evaluated the major claim that paper establishes: the proposed approach can self-adapt to the resource changes. In this experiment, the paper tries to create a real-world scenario by simulating the resource changes over the time. Using the same setting as above, the paper simulates 100 service invocations per time slot. After 230 invocations, the reliability of the first microservice, that is using the temperature sensor deployed on Raspberry Pi, drops to 20% and recovers back to 70% after 430 invocations. Our algorithm starts as usual with the default strategy and generates a strategy at slot 0, which is A, B, C, which means execute all the microservices in sequential manner starting with A. Now at slot 1, the resource change happens and the reliability of the first microservice drops to 20%. And at the slot 2, the system identifies the resource change and changes the strategy using feedback loop to BAC, which means to execute the second microservice first and then go for the first microservice. Now for the slot 2, 3, 5, we use the same strategy, and again at the slot 5, we observe a resource change where the first microservice reliability recovers back to 70%. The system identifies the resource change and hence changes the strategy to the original, that is ABC. Therefore, from this experiment, by switching the strategies whenever it is required, indeed improves the QoS and effectively cope up with the QoS variations in the dissimilar edge environments. In conclusion, prior to this paper, there was a predefined strategies uh, which produced inconsistent QoS with vast dissimilarities in resource availability in multiple edge environments. But the proposed approach dynamically generates strategies using feedback loop and evaluates those strategies using a custom metric called as utility index. So, despite all the unstable and unpredictable nature of the resources in the edge environments, the suggested approach enables QoS-consistent edge services. And one weakness we identified from our side is in the experiments, QoS attributes like bandwidth and power consumption are not considered, which may lead to the challenging trade-offs such as increased bandwidth requirements for low latency. Future goal is that improving the capability of equivalent microservices, that is to handle multiple concurrent service requests on the same resource, which can improve elasticity and reliability of the edge services. That's all we have. Thank you.